Namaste. Welcome to this channel Chemistry Made Easy by Dr. Ashok Mulik. We were discussing last time the molecular orbital theory and we have seen some previous information regarding various aspects, that is crossover of energy levels. And today we will see how is this molecular theory applied to remaining molecules. And we have seen last time the previous molecular application of MOT to previous molecules starting from hydrogen, lithium, beryllium, etc. up to this boron, that is B2 molecule. And now we will see the remaining part of this series where we are considering the n is equal to 2 here. Now we will see the first molecule of this type, that is C2. So for this purpose we have to explain this application on the basis of MO diagram. And what is MO diagram? So for all these diagrams we are not using the 1s energy levels in order to avoid some confusion. So we can show only here if required, or we can also arrange these atomic orbitals. So these are the atomic orbitals of, say in case of carbon, one carbon. Here these are the atomic orbitals of another carbon, and in between them you will have the molecular orbitals of C2 molecule. Now we will have the energy levels of these molecules. So we will have the, say the carbon will provide, each carbon will provide 1s. So these are presented as K. This is K, and which after linear combination gives KK. That is bonding and anti-bonding molecular orbital. Then we will have next energy level, that is 2s. So this 2s has this energy level. So these both are 2s. So after linear combination of the atomic orbitals, you will have the bonding molecular orbital and this anti-bonding molecular orbital. So this bonding molecular orbital is sigma G. We can have this 2s. This is a sigma star U, also having 2s. So 2s squares will produce one sigma bonding molecular orbital, and this is anti-bonding molecular orbital. Then we will have the next 2p levels, 2p orbitals. So there are 3 such p levels. So this we have also 3p levels, that is 2p levels. And as a result of linear combination, you will get this so this is one, this is another bonding molecular orbital, then there is another molecular orbitals, and this is sigma molecular orbital. Now we will label these. These are pi U molecular orbitals. This is sigma G PZ. This is pi G star molecular orbitals, and this is sigma star U 2pz molecular orbital. So we can have the electrons now. If we have carbon, then carbon has electronic configuration 1s2, 2s2, 2p2. So this is lower level and this is valence sheet. So we will mark only valence chain. So valence chain will provide 2 electrons. So there are 2 electrons like this. So these 2 electrons means it will give after linear combination 4 electrons. So 2 electrons will go into sigma G2s and 2 electrons in this sigma G star 2s. Now we will have another is 2p. So 2p has only 2 electrons. So we can show these 2 electrons like this. So these 2 and these 2 gives 4 electrons. So these 4 electrons are filled in these energy levels like this with pairing. Now we can show the various properties. Now you can see this electronic configuration of C2 is given as say K. Then we will have this sigma G 2s sigma G 2s with 2 electrons, sigma U star 2s with 2 electrons, then pi U with these 4 electrons. So this is electronic configuration of C2. Now we can now say this bond order. So bond order is given by, so we can cancel these 2 electrons because one bond is created and this bond is lost because of these 2 electrons. Now we will consider only these 2 for calculation. So there are 4 electrons minus no electron in antibonding MOs. So it gives us the bond order 2. So bond order 2 means here carbon is present as a C2 molecule. But this C2 molecule has very less or rare. It is not commonly encountered molecule. It is not commonly observed molecule. But it occurs only in separate or special cases. So we can say that such type of C2 molecule, instead of occurring the carbon in C2 type, it occurs in the naturally occurring forms like diamond, graphite and fullerenes, etc. Later on again we see that the various ions such as acetylide that is C2 minus 2 minus means the structure is like this. C2 2 minus has structure like this. So this ion occurs in the form of its salts, say with alkali metals and alkaline earth metals. Therefore we can observe its existence also. Then these observations are also supported by experimental evidences that bond distance in case of C2 molecule is 132 pm. In case of this acetylide it is 120.5, and in case of calcium carbide it is 119.1. So presence of such bonds are explained with the help of this bond distances. Now we can have these magnetic characters. So you will find that there is no unpaired electron in these bonding molecular orbitals. So this molecule is essentially diamagnetic. Now we will see another molecule that is, so we will remove this because we are changing these atoms. So now we will take this N2. So nitrogen has 7 atomic number and the electrons are distributed as 1s2, 2s2 and 2p3. So valence chain has structure like this. So there is one more electron added in each atom like this. So there is, but remaining configuration is same like that in C2. Now we are showing one more electron in each of these 2p levels. So there is increase in the number of electrons by 2. So that increased or newly added electrons are going into the sigma g obtained from pz linear combination. Now we can write the electronic configuration of this N2 like this. So you can write this Kk as we have written for previous molecule C2. Then you can write this sigma g 2s, 2 electrons. Then this sigma u star 2s, 2 electrons. Then you can show this pi u and 4 electrons in pi u. These 2 electrons are present in sigma g pz. So sigma g and so in this way you can show the electronic configuration. Now we can have this bond order. So you will find that the bond order is so 1/2 into these 6 electrons minus 0 electron in the non-bonding anti-bonding molecular orbital. So this gives bond order 3, means the molecule is showing the triple bond like this. In this triple bond you will have 1 sigma molecule bond plus 2 pi bonds. So it gives N2 molecule. So their bond multiplicity 3 shows that this molecule is extremely stable, and it is observed with the help of dissociation energy, which is 942 kilojoules per mole. 942 kilojoules per mole is the bond dissociation energy. Similarly, we can have the shielding effect and electron interactions. So you will also see here that there are all electrons in the paired state. So this molecule is diamagnetic. Okay. Now we will see this separation. So if we see the distance between these electron energy levels, or you will find the sigma and this sigma molecular orbitals. So here the distance between these sigma molecular orbitals is larger. It is increased by 12.4 electron volts, which is much less in case of previous molecules like C2 and B2, etc. So this electron in energy difference also shows that compared to B2, C2, this N2 is showing the less S and P characters. Means the mixing of S and P characters is SP mixing is less in N2. Therefore, this shows much less S characters and P characters. So P characters are separately observed here. So this is about the N2 molecule. Now we will see next molecule, that is O2. So this is our O2 molecule. So this O2 molecule has oxygen having 8 electrons, and the electronic configuration is 1s2, 2s2, 2p4. So there are 4 electrons, and these 4 electrons, the one increase the more electron goes in this like this. So you will have these 2 electrons more, and these 2 electrons will enter into these antibonding pi-molecular orbitals. Now this shows that the electronic configuration of this oxygen O2 molecule is, say you can write here Kk, then sigma g, 2 electrons, sigma u star, 2 electrons, then this pi u, 4 electrons, sigma g, 2 electrons, and this pi g star with 2 electrons. So this will be the electronic configuration. Now you can have the magnetic characters. There are 2 unpaired electrons. Unpaired electrons are 2. Therefore it is strongly paramagnetic. So in this way paramagnetism is best explained compared to Lewis's concept. This is best explained by this molecular orbital theory, and this is the greatest success of MOT also. So with this help of this MOT, it also explains, this MOT can also, which is not explained by the other theories. So it is explained by that the molecules like say O2 minus, the molecules like O2 minus, or we will take first O2 plus. So this O2 plus is obtained by removing one electron. So we can write according to the electronic configuration same, but here Pg star will contain only one electron. And this is observed by decreasing the bond order. Here oxygen has bond order of oxygen. What is bond order? You can see here it is 1/2 of these 6 electrons minus 2 electrons. Here in case of oxygen, we are not considering here this, we will consider afterwards. So this will give us the bond order 2. So means oxygen is bonded together with double bond. So here this double bond contains 1 sigma plus we are observing here theoretically 2 bonds, but you will find that this bonding is in different manner. We can show this bond in differently. So one bond is like this and another bond is like this. Means there are 1 sigma plus 1/2 pi bond with pi 1, again 1/2 pi 1. So there is 1 sigma and 2 half pi bonds, and that is why the molecule has specific structure or very interesting structure. Then we will have another molecular ion. So this is a oxygen molecule. Now in this case, in the formation of O2 molecular ion, you will observe that with the removal of 1 electron, the bond order of this increases. You will see that 6 minus how many electrons there is? 1 electron. So this is 5 upon 2 means 2.5. Bond order is 2.5. So compared to this O2, the bond order is increasing here. Again, if you consider the superoxide ion, that is O2 minus, that is superoxide. So in this superoxide, 1 electron compared to this, 1 electron is more like this. So we can calculate this bond order in this way. So 6 electrons minus, you will have 3 electrons. So this gives us 3 upon 2 means 1.5. The bond order is 1.5. And this is also explained by the bond distance. In case of O2 2 plus, here the bond order is 2.5 and therefore bond distance is 12.3. In case of oxygen, this because of double bond, the bond distance is 120.07. In case of superoxide, because of the bond order is 1.5, the distance is 128. And again in case of O2 2 minus, the bond order is, means there is increase in again 1 more electron. So you will have the bond order like this 6 minus 4. So you will have 2 upon 2 gives 1. So bond order in case of O2 2 minus is 1. So this is supported by the bond distance 149. So with decrease in bond order, the bond distance increases. So in this way, we can explain the various properties. So with this we will stop our discussion and we will continue our discussion in the next lecture regarding these F2 and Ne2. So please subscribe to this channel and please press the bell icon and like button. Thank you very much for watching.